So we're starting with the next talk, NFV and SDN, Architecture and Optimizations for the LTE and 5G Wireless Network. The presenters are Krishnamurthy and Sumesh Subramanian. Krishnamurthy Jambur is a network software engineer working in Intel for 12 years with experience in working on network processors, Linux kernel, real-time virtualization, Intel microarchitecture performance optimization, multi-access edge computing, and containers. He's interested in the low latency real-time system designs, 5G access and edge cloud, hardware offload, and data plane. Sumesh Subramanian is a senior wireless software engineer working in Intel with 10 plus years of experience in wireless technologies on custom ASICs. Currently leading FlexRAN software program and focusing on L1-PHY implementations of 5G and 4G networks on Intel architecture.
So good evening, everybody. My name is Sumesh Subramanian, and I have my colleague here, Krishnamurthy, who will also be talking. So we are sharing this 1 hour period for talking about what we are doing in the wireless space. So both of us, we work in Intel. We've been around 10, 12 years in this company. So we work for the DCG group, which is a data center group, specifically under NPG, which is Network Platforms Group, 5G ID, which is 5G Infrastructure Division, and Software Wireless Access. So today, mainly, we're going to be talking about software wireless access. So maybe can I get a show of hands of how many people understand what wireless access space is? Okay, that's quite a few hands. Okay, so when we say wireless access in our group, we are not talking about Wi-Fi or Bluetooth. We're basically talking about the 4G and 5G networks, right? What your service provider is giving you as connectivity. So this is what mainly we're going to be talking about. So I'll be talking about, I'll give a brief introduction into the wireless systems and then also talk about our FlexRAN system, right? And then Krishna will take over and talk about NFV and SDN and what we're doing in that space, and also talk about MEC, right? And then we'll go into our demo and our live demo and what we have today in Intel for this wireless space. Okay, so this picture, this is aimed at basically giving a very high-level view of what is happening in the wireless world, what is happening traditionally, and what's coming new to the market, right? So over here, I basically plotted out what is the wireless core and what is the wireless access, right? So in the wireless core, you have this entity called the EPC, which is the Evolved Packet Core. It's basically the entity that's facing the internet, and then and the other side it's facing the wireless domain. So it's responsible for getting all the data from what the user is requesting from the internet or from the private network or whatever, right? So this entity is usually maintained by your service provider, and it's sitting in their core, right? And then there's this new concept called MEC, which is mobile edge compute. So where a lot more workloads are being taken away from the data center or from the internet and trying to be moved closer to the edge of the network, right? So this is a very new kind of thing, and people are trying to deploy this. And then finally, you have the eNode B system, which is your base station, right? So typically, there are multiple eNode Bs talking to the EPC, and your eNode B is usually towards the edge of the cell. So, yes.
The official name is multi-access.
Right. Exactly. Yeah. So there are multiple names. Yeah, but you're right.
Can you repeat what is?
Yeah. So he just pointed out that MEC stands for multi-access edge compute, right? And then finally, the eNode B system, which is your wireless base station, which is giving you connectivity to all the users that are connected to the eNode B. And this is closer to the radios, right? So this is at the very edge of the network, right? So this is how a traditional network looks like, and then this is what is happening new to RAN. So there's one disclaimer. So the wireless world is pretty notorious with abbreviations. There are tons and tons of them. So I think we are going to share these slides with you guys after the presentation. So we have put up a glossary with most of these abbreviations. So, and we'll try to expand on most of them, right? So RAN basically stands for Radio Access Network, and it's basically the eNode B. So there are multiple names for the eNode B. It stands for RAN, ENB, eNode B. People call it in many names, right? So what is coming new to RAN, right? So what people are saying is, so traditionally again, this is sort of centralized. The EPC is a centralized function. It's sitting in the service provider's core. And then the E node B is all sort of distributed. It's sitting next to the radio heads, right? So now what they want to do is try and centralize some or most of the E node B functionalities into a data center, right? And then drive only the radio traffic towards the radios, right? So with this, you can do a lot of different things, like you can do small cells of mini cloud RAN, all these kinds of deployment scenarios are possible, right? And I'll go through a few more slides as to how this is helpful. But this is what is new to RAN, right? So this is how the network is evolving, and this is what the service providers think they want to be doing. Yeah, and like Ray mentioned, we would like this to be interactive. So if you guys have any questions, just yes.
I have a question. You're showing MEC north of the Sierra.
Right.
There are a lot of talks about having a base station next to radio heads.
Right.
So what's your opinion? Where do you see it coming?
Right. So Krishna is going to talk more about MEC. So yeah. So the question was, I guess the MEC is going to be close to the base stations, right? And then we are also saying the base stations are going to be close to the radios. Yeah. So Krishna will be talking more about MEC, but yeah, the idea is to have the MEC close to the E node B, right, or close to the RAN, so that you can offload most of the traffic, or you can build apps on the MEC infrastructure itself. So this reduces latency, right? You don't have to go all the way to the internet and then come back.
Now what you are showing is 15 kilometers away over C3, right?
Right.
What being talked is being within meters of connectivity.
Right, but the CIPRI is, although the CIPRI is far away, you still have to meet your 1 millisecond latency and things like that with your A node Bs, right? So you're not going to be adding a lot of latency to the CIPRI itself. But since this guy is going to be sitting next to the E node B, he does not have to go, if you have an application, or if you have a user that's getting some application, let's say from YouTube or something like that, right? It needs to go through a lot of hops, and by the time it comes back, there's a lot of latency. Right? By caching some of that YouTube content, I'm just giving an example, right? In an MEC kind of thing, you avoid going all the way to the end of the core and then come back, right? So those are the kind of applications that people are talking about. Yeah, does that answer your question?
No, my comment that you're showing it too far away.
Right.
It's actually much closer to the user.
Right, it is. I mean, I guess it is close to the E node B, right? I guess this line is wrong, but I mean, there's not a lot of distance between the MEC and the E node B itself. It's right next to it, right?
The BU hotel is in general in radius of 15 kilometers from radio heads. So you're 50 kilometers away from the head, which is significant.
Right. But again, we are saying that the E node B functionality is pretty close to the MEC, right? So in this picture, don't look at this picture, but in this picture, the MEC is going to be sitting probably in the same data center as the E node B. So it's going to be right next to it. Right? And then you're driving this radio traffic over simply to the radio. Yeah? Okay, so this slide is talking about the deployment evolution. So again, so the EPCs today are sitting in data centers. They are running on Intel architecture, right? And then you have Ethernet backhaul for all of your IP traffic to your cell site where your E node B is running, right? So you have layer 1, layer 2, layer 3, transport network layer, all of these things sitting right at the cell site, right? And typically traditionally what people have been doing is they have custom silicon, custom SoCs for the E node B functionality itself, right? And then the next generation networks, what they are saying is they want to try and take out this E node B piece from the cell site and try and move it closer to the data center, right? So you have more workload in the data center, and you just have to transmit IQ samples or radio data all the way to the edge of the cell. And so what does this help with? So with the custom solution, obviously you have a lot of CapEx, OpEx. You need to build something specific for the network. With this kind of solution, when you move things to the data center, you want to run these kind of applications on COTS hardware, right? So already there's a lot of investment in the data center by the service providers, so they want to try and run these functionalities here. And it also, you can make use of virtualization and other IT deployment things that are already available out there into this kind of wireless space. So this is what people are thinking, right, in terms of deployment. And because of this, the network is also evolving, so the standard bodies are also evolving. So what I'm showing here is a deep dive of the RAN, or the eNodeB itself. So if you split it out into these blocks, so all these blocks here in green are part of the eNodeB itself. So you have this RRC entity, RLC, MAC, and PHY. And then there's RF here, and then the core network on the other side, right? So, sorry. Yeah. So the RRC PTCP is an L3 functionality, MAC RLC is L2, and then the L1 is basically the PHY, right? So when I take an example of today's network, let's say a 4G LTE network, and I take a 20 megahertz 2x2 cell, the throughput, in ideal conditions, when the channel condition is awesome, the throughput coming all the way from the EPC to the user is in the range of 146 Mbps at this interface, 147 at this interface. All the way here, it's around 2 Gbps of traffic. Right? There's a lot of data being transferred at the PHY layer itself. And then in terms of latency, you can tolerate within 100 milliseconds of latency between these two interfaces, and by the time you come here, it's in sub-milliseconds. So this is your 4G network today. And with 5G, what's happening is this number is going up. It's in the order of 10 Gbps and stuff, that's what people are saying. And this number is coming down. It's going to be like 0.2 milliseconds at multiple standards coming down. Oops. Yeah, so there's a lot of complexity that's growing, and then there's much lesser time to do all this work, right? So 5G networks are getting more and more complex. So again, reiterating the previous slide, we have the core network, and then this entire stuff is running right at the edge of the cell, right? So this is what is called as a distributed eNodeB kind of deployment. Now, the standards have started evolving, so what they are saying is you can start splitting all these layers with all of these kinds of latencies present, and then try to centralize move most of these things towards the EPC, or sort of not towards EPC, but try and centralize these things, right? So you have all these different kinds of splits where you can split the PTCP. The data moving here is still, some kind of proprietary APIs and whatever, but they want to try and split these things, right? So so the service provider now has a choice. So they basically can choose one of these kinds of splits and figure out what works for them in their network and try and deploy this, right? So what we're trying to show here is with this kind of thing, building an ASIC or an application-specific processor for each one of these models is probably not going to be feasible, right? And if we do all of these, if we can support all of these kinds of things in software, you have the same kind of a hardware platform, and you can run all of these kinds of modes, right? So that's where Intel is driving, right? So that's where we in SWA are trying to say that, okay, we can sort of prove all of these kinds of modes, and then the end customer can pick it up and try to do something with it. So, yeah.
So split means you're splitting the left-hand side functionality on the basic and the right-hand side.
No.
What is the split?
Right. So the split here literally means that these functions can be separated away from these functions. Right. That's what we mean by split. So they could be sitting far away, and these could be sitting far away.
Like
But physically, right? But the problem is you will start having problems with these kinds of things, right? The latency, the tolerance here is 1 millisecond. So if you keep it really far away, you're not going to have a good link, right? So there are challenges, obviously. If you go to a split like this, you can't go too far away. You probably have to be very close to each other. But yeah, so what we are saying is you don't have to build a custom solution for each one of these models, right? Yes.
And you're not splitting, you're splitting the entire box, is not partially, right?
Right, exactly, yeah. Yeah, the functionality within those boxes.
Can you repeat the question?
Oh.
Sorry.
So the question was, are we splitting parts of this box or the entire box? So the standard has defined functions within each box, and that's what can be split.
In the Cloud Run architecture, the big problem is the latency between the RRU and the BBU.
Right.
So is there any dynamically change between this dividing to, for example, if the bandwidth is low, so can we use the physical network function increase capability?
Right.
Or can we choose how can we split it?
Yeah, that again, if So let's say you split at this layer like this, right? And you put some software-defined piece even towards the RF, then all those kinds of things are possible, right? As long as it's software-defined. But as soon as you put something specific, let's say you're running only layer 1 towards the RF, then it's very hard to bring in layer 2 if you want to, right, based on demand.
Yeah, but what I know that maybe I'm wrong, but the big problem is in the FlexRAN, there is no definition with how to split architecture. So is there any working progress on it? So how we split the architecture layer by layer?
Right, so what we are doing is we partner up with a few other companies, right? So there are certain companies who have such blocks here, and they have very good split within those layers themselves, right? So what we try to do is, let's say they have Ethernet protocol between these two, and they have some special APIs themselves, right, to communicate with each other. So we try to split them apart and try to see if we can communicate over Ethernet, right? So there are a few splits, like we work with certain service providers, for example, they want this kind of a split, right? So in our group, at least in FlexRAN, this is what we are concentrating on, this kind of a split, right? But there are also certain questions where people want to split here and see how that works out, right? So yeah, I mean, we are trying to address all of these things, but it's based on what our customers are asking us.
Okay, thank you.
Okay, so that was just a very high-level overview of what is happening in the wireless space and how it's evolving. So next we will go into FlexRAN, right? What exactly is Intel doing in this space? That's what these set of slides are going to talk about. What exactly is FlexRAN? So it stands for Flexible Radio Access Network. So in a gist, it's just a wireless base station running on IA. That's what we mean by it, right? So as soon as we say running on IA, you get all of these things like scalability, flexibility. It's a software platform with optional hardware acceleration. You could put FPGAs on PCIe cards and accelerate certain functionalities, right? And yeah, so all of these kinds of things are possible. That's why we call it flexible, right? So what exactly is this? So what we are doing is we pick up a standard COTS hardware. It's commonly off-the-shelf available hardware. So like one of the platforms that we are showing here in our demo. And what we are doing is, at least in our group, in my group, we look at the layer 1 piece. The layer 1 piece is probably the most cycle-intensive and MIPS-intensive part of, again, getting a 15-minute warning. Yeah, MIPS-intensive part of the entire RAN functionality. So we are trying to optimize that into IA and provide that as a solution to our partners and customers. So they can use these optimized functions and plug it into their, their software and try to see if they can port it as well, right? So we build a reference software. And then on top of this, we also define the operating system, right? Like I said, the wireless space is a very low latency kind of thing, right? You're talking about sub-milliseconds and a lot of throughput and stuff like that. So we work very closely with our vendor team, and then we feed in a lot of inputs and try to reduce the interrupt latencies and things like that to help us make these workloads possible in IA. So again, by doing something like this, you could run a RAN, which is your layer 1, layer 2, layer 3. You could run the EPC, which is all of these components, or you could also run an NEC kind of an application, right? So for an operator, he just has to buy a rack and then deploy multiple VMs, or run the same kind of workload on the same VM, stuff like this, and it's the same platform, but he can run different workloads, right? So that's what we are trying to do. And then at the other end, you have these RRHs, radio heads, right? Typically, there's a protocol called CPRI, which is Common Public Radio Interface. So most of our radio heads follow this protocol. So we have FPGAs that are connected over Ethernet. So this FPGA is basically converting Ethernet to CPRI and so on, right? And in the future, moving forward, there is something called radio over Ethernet protocol that's coming to these radio heads itself. So it's probably going to be just an Ethernet interface going all the way to the RRH. Right, so in a gist, this is what FlexRAN is, right? So this is what we are showing also in our demo today over here. Okay, so this diagram is talking about the layer 1. So again, in my group, we work on layer 1, so we wanted to show what exactly are the challenges, right? So this is a typical flow of data in the layer 1. So this is downlink, meaning data moving from the eNode B to your device, right? So there are all of these blocks. And then this is uplink, meaning data coming from your device all the way to the eNode B, right, the other direction. So there are many blocks here that are very cycle intensive. It's not very easy to run all of this in 1 millisecond TTI and things like that. So what we also do is we offload certain things to FPGA. So we work with our PSG group, and we try to offload certain functionalities into FPGA. So these are called the front end pieces. Again, if you remember from the slide, these are part of the lower PHY, right? So the throughput at this interface is around 2 Gbps. At this interface, it's around 1 Gbps, right, per antenna. So so the throughput also reduces, and you remove some complexity also towards the radio head. So again, a lot of our customers are asking this kind of a thing, right? So we work on these kinds of things. And also, there are 2 other blocks, this turbo encoder and turbo decoder. These are bit operations, very cycle intensive. There are a lot of loops, a lot of iterations, right? So again, in a traditional device, even in a DSP kind of a thing, they build hardware accelerators for these, right? They don't just run it in your DSP. So again, what we do is we're trying to take some FPGA and try to offload these things. There are a lot of customers asking us to do this. So we call that a look-aside FPGA. So it's basically a PCIe plug-in card, and we try to offload this onto that. And then my final slide. So this is what we are doing from a FlexRAN to help our ecosystem and partners, right? So we define the platform. So today we are running on our current Xeon platforms, and then we also work with our FPGA group to define IAA plus FPGA. And we also feed into our next generation Xeon processors as to this wireless workload, so they can build some instruction sets and stuff like this to enhance, right? So we will be capable of doing wireless workloads more efficiently on IA. And then from a software perspective, we do provide drivers, platform support, framework, which is the BBU pooling piece, all of this kind of SDK kits. So again, our customers can pick it up. They might not want to use our entire FlexRAN solution or 4G or 5G solution. They might have their own magic recipe, right? But we provide these tools, and also this SDK with these optimized functions, like things like IDFT, IFFT, FFT, which does not have any magic recipe, right? We provide these to our customers and enable them to get to market quicker. So that's one of our things. And finally, the LTE releases, right? So currently we have a complete 4G, 3GPP release 10 compliant software running there. And we are also looking at 5G TF and 5G NR, which are the new 2 standards coming out, one driven by Verizon and one driven by 3GPP itself. So we have started doing some work in these spaces as well, and we are providing optimized tech. Then we have a group where we have an end-to-end kind of a demo with 5G in our labs, but it's very rare. We can't just bring it over here. So we're showing a 4G demo here. Yeah, so these are all the slides I have. So
do you want to take a couple questions? Or
yes, exactly. Yeah. So if you guys have any questions, yes.
Where do you expect money to come from?
Sorry.
Obviously, you want to sell hardware. RAN is a killing business. Sometimes single-digit margins. What are you going to sell besides hardware?
That's a good question. Yeah, it's mostly hardware. Right? So Intel is all about hardware. So what we are doing is we are not selling software. We are enabling our customers by building reference solutions. So our charter is 2-tier. We do these kinds of POC kind of things. We go to the operators and say, hey, we have a working solution in IA. Right? And then we work with our partners and other tier 1 customers to enable them to go to.
So the expectation from customers is to get software for free, just as infrastructure.
Oh, yeah, for us, yeah, I mean, we just give it for free. Yeah, there's a license, of course, there's an NDA license, but yeah, we would like it to run on IA, right? So that's pretty much our requirement.
Okay.
Any other questions? Okay, so I think I'm over. Okay, with that I'll hand it to Krishna, and he will talk about the next few slides.
Okay, so we will now look at some of the wireless use cases. So we looked at the FlexRAN architecture and how challenging it is, and we now need to understand how do we address these challenges and still show our NFV use cases and still show what the typical gains from SDN and NFV deployments. So the kind of work that we do in enabling customers with virtualization and SDN use cases are broadly classified into these 3 groups. So we enable customers to transition from custom silicon or custom hardware to Intel architecture and help them achieve higher performance, right? And we also develop proof of concept which demonstrate effective platform utilization, because from ASIC world they are sort of dedicated hardware which cannot scale. That's the biggest one of the biggest disadvantage with ASIC. And what we are showing here is that on a Xeon multi-core environment where there is plenty of cores, I/O and memory bandwidth, how do we effectively utilize and still achieve flexibility? And lastly, develop optimizations for infrastructure. See, at the end of the day, when customer wants to deploy a base station in virtual machine, they need to find a path such that whatever data is coming today through the network reaches them quickly and deterministically. So if the path is bumpy or having a lot of issues, then that's one of the demotivating factors. So we try to address those blocks or challenges in NFV infrastructure, because some of the things that we saw when Ray presented, there are certain network elements that can take advantage of classical Linux KVM infrastructure. Then you start putting these real-time ASIC workloads in a virtual machine, the challenge completely amplifies. And we are trying to address that by optimizing the NFV infrastructure so that customers don't need to go through this, but rather think and work about their workloads. So going back to this diagram that we showed earlier, so we will look at some of the challenges and what the solutions that we developed, right? So why would customer typically want to move to IA? One of the reason is densification, consolidating the stacks, having most of their workloads in virtual machine, and also in a sort of a densified platform such that you have higher gains by deploying such solutions. So one of the challenge here is that you have virtual machines, each having their own characteristics, and then we also saw this split, and even with that split, we saw that some of the components on the right hand side were packet processing oriented, some of them on the left hand side were real-time low latency oriented. So when you have these virtual machines here, for example, L1 is latency, L2, L3 is again latency plus packet, and you have your transport. This is your TCP or IP stack, and then you have your apps. So each of these have different characteristics, and now you start consolidating on a single server or single architecture, you start seeing challenges. And we try to demonstrate this through various mechanisms. We use platform enhancements, so we get to understand the issues from customers and try to incorporate them in silicon and then expose it through Linux KVM. So some of the standard things that we have done include Intel RDT, which is resource directed technology, where you can separate cache, separate memory bandwidth, so that you can achieve deterministic performance. Second is efficient utilization of resource. So having multi-core is one thing, and you want to use those multi-core in an efficient way. For example, you have your layer 1, and all of a sudden, for example, let's say there is a game, and that base station is experiencing higher bandwidth. Now you want to allocate more cores or resource to this virtual machine for that duration, and then remove the resource and allocate it to somebody else, or shut it down to save power. So what we call as dynamic resource allocation is one of the use cases that we work on to demonstrate, still by achieving all those latency numbers and all those throughput numbers. So scaling, flexibility, still meeting all your LTE and of course the 5G performance requirements. Next is the deterministic execution. So any event that happens on the platform needs to be delivered to virtual machine as quickly and as deterministically as possible. This includes timers. For example, somebody does a delay or a sleep, and then he needs to be woken up deterministically, because if he wakes up with higher latency, or what we call as jitter, then he misses the entire processing deadline. So we make sure that all those platform events reach the user space where the workload is actually there, and he can execute the rest of his job. Lower latency for VM to VM communication. So we look at the splits, and we also saw other splits in previous slides. So once we have splits, that means that there is also a requirement for east to west traffic. That means L1 virtual machine wants to talk to L2, L3, and which ultimately wants to talk to transport layer, which will send out the packets, which will be consumed by your apps. So what we call as east to west traffic, and we need to make sure that they are deterministic. We don't have bottleneck with, for example, vSwitch and interfaces. So we work on optimizing not just the software components like vSwitch and vHost, but we also work on optimizing the Intel network cards and switches. So deterministic VM live migration. So once you achieve this, the next challenge that typically operator asks us is, so for example, we want to consolidate all the network elements that are running on multiple chassis to fewer, for example, during night time, and then spin them up or bring them back to their original status in the morning, right? So for those cases, typical data center mechanism is live migration. So without bringing the cell down, you want to move the virtual machine from one platform to another platform. So we have demonstrated that using higher layer protocols. L1 is challenging because there are still a lot of signaling happening even though the users are not connected. So we have demonstrated that this mechanism of live migration of higher layer base station layers, for example layer 3, across platforms with VM downtime, which is far lesser than what you see in data center today. And of course we have SDK for apps development, which we'll go through. The last one is, so ultimately at the end of the day, you want to have deterministic end-to-end latency. So there are certain things that Intel can do on the platform and the infrastructure, and there are some things that we need to work with our community. And we are trying to make sure that there are no bottlenecks here on the solution space on the server side and also on the IO side. So we are working with operators and telecom equipment manufacturers to see how this future interfaces can help us enable such deployments. In the next slide, we'll look at the use cases and looking through the lens of our FlexRAN architecture. On the top, you see the end-to-end pipeline of FlexRAN, right? So, which we saw earlier. You have remote radio heads, and we have a front-end device that terminates this wireless streaming protocol called CPRI and converts it from time domain to frequency domain, and then also does some amount of layer 1 processing, and then sends the packets to our servers. So the server is here now. So, and within the server we have demonstrated virtual machines for base station where L1, just L1 is in separate VM compared to L2, L3, and or a mechanism where the entire L1, L2, L3 is in a single virtual network function. So the optimizations and the use cases that we have done are reduce platform latency for 5G. So we take this DPDK as the base and try to make sure that if customers start using this DPDK to build the base station, they have a better mechanism of getting packets because DPDK is pole mode driver. You would like to have deterministic packets, because doing vector processing or burst processing is good for most of the packet processing workloads, but for real time you need to be aware of certain things that you need to take care of. So we make sure of that, and we look at how do we reduce the overhead on CPUs so that the CPUs will be available for customers to do their packet processing by, for example, we offload certain parts of vSwitch and pre-classification for MEC onto the NIC, which is Intel Network Interface Cards, which has flexible filters, so that when the packet arrives, they can arrive in such a way that they are automatically load balanced or distributed across multiple queues. So the workloads can start using those packets from those queues, which means that they have better cache efficiency, then you get better performance. Next is the scaling, which we talked about, which is dynamic resource allocation. We have mechanisms where the FlexRAN stack that we have developed can add cells dynamically and remove cells dynamically, which in turn makes removing of cores allocated to the virtual machine, which is also dynamic. So ultimately this means that we can save power and we can also load balance the resource on the platform. So along with virtual machine deployments, we also look at container deployments. We are evaluating multiple architectures. We don't want to put a huge virtual machine in a container just for the sake of containerizing it. So we need to look at what is the real architecture split and gain, and then start containerizing those sort of modules, or what we call as microservices or RAM. So once we do all these enhancements, we also want to make sure that these enhancements are exposed to the higher level orchestrator and OpenStack. So we do that by working and exposing those APIs to OpenStack. We are also working with multiple orchestrators so that these enhancements are available for customers to sort of orchestrate a FlexRAN-like solution. Lastly, the live migration use case that we mentioned, so that we can migrate the virtual machines between platforms to achieve consolidation. So most of these use cases that we work, we make sure that they are available as close to commercial solution with Wind River Titanium Cloud, and also we make sure that it is upstreamed through OP-NFV projects, through KVM for Linux, where we have a real-time work group and all these optimizations are upstreamed. So lastly, we also make sure that we use the FlexRAN for end-to-end test beds, both for validation and demonstration. And we have one here today, we'll go through that. So looking a little bit deep into the NFVi stack and how it looks. So we have today, we use Wind River Titanium Cloud 3, which is a carrier grade network environment. And following are the important components that really enable us to run layer 1 like workload in virtual machine. That includes like the real-time extension, low latency and carrier grade. We also have this is the requirement from the stack itself. So if you don't meet your timing, then your eNode B doesn't even work and the users can't even connect. So we have near native performance. That means when you virtualize your layer 1, the performance difference from running this workload on bare metal Linux compared to virtual machine is it's nothing today. So we have optimized that in such a way using both the Wind River Linux environment and also the enhancements that we have in the silicon. So this includes near native performance for interrupts and whatever we call the infrastructure events, and also the stacks. We also have multiple cell support We can run a single cell in a single VM, or go all the way up to, for example, 8 cell in a single VM, and also we can run 2 by 2, 4 by 4, and in whichever sort of dimensioning that you would need. And we also optimize data path, and that would also be a sort of a reference for customers. And how do we handle packet forwarding and pre-classification for both RAN and MEC? So the architecture for NFVi is same, and this enables us deploying both base station along with our MEC applications. So these MEC applications, if they are closer to the base station, then they can take advantage of multiple things, which are like, for example, user information and what we call as RNIS, which is called radio network information. So the apps being closer to the base station can service the users more intelligently compared to the same apps being in data center. So lastly, because everything is implemented in software, it can scale all the way from Atom to Xeon, and even within Xeon it can support Xeon D, Xeon SP, and Xeon AP. So the infrastructure also supports mechanisms to offload to an FPGA, which is again visible through your OpenStack. So the infrastructure is today ready for deploying such solutions for 4G. So in order to achieve this sort of performance, we had to do a lot of optimizations. And these optimizations means that we need to use a lot of tools. So Intel has a very rich set of tool sets which enables customers to understand what is the current performance, where is the bottleneck, and how do we address that. So some of the tools that we used in FlexRAN include the vTune amplifier and inspector, which analyzes where is the hotspot in our stack and then try to address them so that you see better gains. And then we also use math kernel library here, which has some of the DSP functionalities which are provided to you out of the box. We also use Intel compiler ICC because this enables us to use instruction sets like AVX 512 and AVX2 to implement some of the low-level math algorithms like IFFT and IDFT, like IDFT. The tools also has a mechanism for taking advantage of multiple cores by doing multi-threaded programming. So TBB is such a framework which is available out of the box. We use, in FlexRAN, we use DPDK based architecture, which is mainly pthread based. So let's switch our attention to MEC, which is multi-access edge computing. We have an SDK, Intel provides an SDK for operators and application developers to kickstart the application development and also do some trials with MEC. So we call that as Network Edge Virtualization SDK. So we have gone up to 3 releases now with this SDK, starting from Atom, and today we are supporting Xeon and Atom. We provide out of the box eNodeB and EPC environments using Polaris emulator, and we also provide tools. And so we basically provide a sandbox here where the entire infrastructure is ready for an application developer to just drop his app into a virtual machine. And once he does that, he gets all the interfaces that HC MEC defines. And this includes REST API. So for example, a video transcoding application here can request for resources, request for what the standard MEC interfaces that are defined by HC, and he can get it. the SDK itself makes it transparent such that MEC can be deployed on S1 interface or SGI interface. We support VLAN and we also support complete OpenStack environment. For application developers who don't want to have this setting up the complex OpenStack environment, we also have a small footprint CentOS based environment where the requirement is just a single DPDK port so that you can get all the traffic. So if we look at the, so we closely use the HC MEC architecture to do this. Yeah.
You have a solution to mobility events in NET, synchronization between different.
Do you provide any solution in case of mobility event between NECs?
Yeah. So mobility event in MEC is one of the challenging aspects. So the question comes here is, for example, you have an app and which is being serviced by a particular eNode B. So you have a user who is trying to use, for example, an internet service, and it is going to an eNode B and it is going to a MEC app, and that user moves and the eNode B handover happens. So how is this handled by this MEC app? So the path that we have taken here is we want to be as close as possible to what HC MEC defines. So the interface for handover for HC MEC is, they don't want to define it. So there can be a custom interface because there are things like N-to-1 or N-to-N interface. For example, N number of eNode Bs can be connected to a single MEC platform, or multiple MEC platforms can be connected to a single eNode B. So depending on such deployments, it's up to customers how to handle these mobility events.
But you see, that's the problem, right? There is nothing in definition, and you need to optimize. If you keep it generic, the time to move, to share state, share memory.
Yes. So I think the challenge here is, it depends on how a customer implements. For example, the mobility event that the eNode B gets can be shared with the MEC platform. So, but this event of mobility, which is for example over X2 interface, needs to be somehow communicated to the MEC app. And this interface is what HC doesn't want to define. And they have left it as an open interface for implementation. So handling this in SDK is a bit tricky because it depends on what that eNode B does. So in this architecture, what we see here is the green blocks that are provided as part of our SDK, which includes OpenStack, data plane. We provide MMFi APIs, which are closed or looks like XCMEC because it's just now defined. So, and also we provide MP1 in APIs. We also have policy and registration where policies for the apps can be configured and the apps will start using those. Right. So this includes, for example, the mobile edge platform manager will deploy, for example, a UHD app, which is servicing a user with the UHD content. So he will set rules on what users traffic needs to be sent to this UHD app and what users traffic needs to be sent to EPC. So all those can be done using our SDK. So just to summarize, so this is how it looks like with all the components in our SDK. So the orange blocks are the ones which come as part of Wind River Linux. So the blue components are part of MEC deployment. So we develop it on top of DPDK, and we have hardware abstraction. I'll just get to it. And we support S1 interface and IP interface. This is the data plane. And we have an OpenStack controller here, along with the MEC platform manager to deploy MEC apps and also configure policies for them through the service registry. So the first deployment is on S1 interface. This is a MEC box in between eNode B and EPC. So this is S1U GTP traffic. So we have configuration here. When the GTP traffic comes in, we extract the IP frames and send it to the app. So the app, for example, a UHD app which has been developed, who is looking on a socket, he gets this IP datagram. So it's completely transparent to him, and he needs to just make sure that he calls these APIs. Yeah.
What happens if S1U traffic is encrypted, like in Germany?
So S1U traffic, again, we make sure we follow what HCMEC says. So according to HCMEC, the encryption is out of scope. So it is understood that the MEC deployment or the MEC apps is somewhere which is deployed next to an eNode B or closer to eNode B or closer to eNode EPC or an environment where it is what they call it as where the security is controlled, or in the sense that what goes into the platform is under the control of operator. So there can be key exchange, or there can be a network element here, for example, transport layer, which decrypts and sends clear text to this MEC routing. So the second deployment is through the IP interface. So you can just even look at this. So this is when you have your eNode B and EPC also. So with 5G, to address the low latency, the new trend or new technology enhancement that's coming is also called as distributed EPC. So in distributed EPC, you have user plane of EPC also closer to eNode B, so you get clear IP text packet and we send it to the virtual machines. So this means that we can also aggregate traffic from Wi-Fi interface and also service them, so that LTE Wi-Fi is sort of transparent to the application developers. Lastly, local breakout. For example, let's say this is the UHD app and it's in a VM and he needs a lot of horsepower, and let's say he wants to access some of the graphics acceleration. So in this case, he can configure the data plane such that for a set of users, we get the traffic, and only those users who are serviced by the MEC app, he can automatically redirect it to a set of servers here, which actually does the processing, and they send back the traffic. So this is what we call as local breakout. This also means that you can have your public cloud today from various vendors that we have can be deployed here. So now we will switch our attention to this demo setup. So in our demo today here, we have end-to-end network, LTE network with FlexRAN being the core of our discussion today. So we have a Xeon platform here, which runs FlexRAN, and we also have EPC. So, and then we have a drone which is capturing video, so we can switch to that. There you go. Yeah. So the drone which is here, which is blinking, it's transmitting the video, transported video. So we have an Atom processor here which is capturing the video from these cameras, and it is transcoding and sending Ethernet samples to EPC. And EPC is sending, the P gateway is sending the traffic back to the eNode B, which is running on this server, which is a Xeon server, Xeon D server. And here we are running FlexRAN. And what we do in this is we are basically doing downlink. So we do all the LTE processing on downlink, if you guys remember what we showed in the previous slides. And then he sends it to a front-end device, which is an FPGA, which is built on Altera FPGA. So the data from here to the FPGA is over Ethernet, right? And from here, he converts the Ethernet to CPRI and sends it to the remote radio head. This is the remote radio head, and from remote radio head, it goes to a LTE user equipment, which is this laptop using the LTE dongle. So we have end-to-end architecture using end-to-end LTE demo using Intel architecture, and there is nothing preventing users or customers to scale this to, for example, to have different splits, or even sort of having in a typical enterprise environment, having both EPC, distributed EPC and MEC app and base station on servers like this. And also, if you can, I mean, after this demo, you can also look at the form factor. It is a low profile, single U platform, which has capability to run multiple cells. So, and in this, we are not using any accelerators. Any questions?
You mentioned you have NFV. It is based on functional split, or for the NFV is this based on functional split?
Yeah, I can repeat. So the question is this E-node-B based on functional split? Yes, this is the split PHY processing, where a part of L1, which is what we call as conversion from time domain to frequency domain, the FFT is happening on the FPGA, and rest of the processing of L1, L2, L3 is happening on E-node-B in a virtual machine. Yeah.
So for the lower PHY is after resource demapping.
Yes. Okay, so if there are no questions, thank you very much for listening to us.